Today's 21, 1, and we're going from 10 to 11. And I got somebody there, maybe. I don't know. Hope that's right. I do. Morning, Aunt Sophie. Hey, all right. And okay. That's Teresa. Teresa, thank you. We understand. I'll try and hope it records everything today in case you get cut off. And Ellie, good morning. So when we got Zach, we got everybody. Let's see if Zach gets here. I hope so. And what we're going to do this hour is more on harmonic motion, but first we need to talk about something called Hooke's Law. And I brought some stuff from school to help us with that. But I may get that out first. Okay, well, I'll decide. Oh, I got a fourth. Maybe I got Zach here. How about I ask? Earth to Zach. Come in, Zach. No, not yet. Okay, well, hopefully Zach will join us. We're going to go ahead and start up. So, yeah, here's the deal. First off, let's review just a little bit. Remember last time we had like, well, I got a mass this time. Here we go. I'm going to make this into a harmonic oscillator because I brought this from school. And there we go. So I got a pendulum, right? It's not perfect. This should be a piece of string here. It's a little rigid. It's metal. But you kind of get the idea. So back and forth. Remember we said the middle was an equilibrium position and that harmonic oscillators are symmetric on either side of that position. So they're symmetric in and So can you look back and remind me? In terms of the equilibrium position, harmonic oscillators go back and forth and they're symmetric in and on each side. What were they symmetric in? Just to check and see if you got it. Distance and time. Thank you, Ellie. Super. Good. Okay, so the same amount of distance on each side and same amount of time to go out and back. And then we had a special out and back thing. The time for one cycle, one complete out and back was called a period. So, and Teresa's there too. Good. All right. So a period is the time in seconds. So out and back, that would be one period. And I can also talk about a cycle. So that would be one cycle, or I can go through a bunch of cycles. Maybe this has a bunch of cycles every minute. Okay. So out and back trip. An out and back trip is a cycle in physics. Okay. But the motion doesn't have to go that way. And what you can do instead is ta-da, you can have the motion go up and down. Aha, so I got a different harmonic oscillator here today. Hey, Zach is there. Super, thank you. Glad you could join us, Zach. We're complete. Our total physics is totally there. Okay, so this is a little long. Maybe I got to back up a little bit. There, now you can see it. And so I'm going to make this thing oscillate. Ready? So it goes up and down. Okay. And so now, instead of going back and forth, I got a different oscillation, right? My oscillation, my cycle is more or less down and up and back to the middle. So I'm going to leave it there for a second, and we're going to claim that that is our equilibrium position, right? But for this harmonic oscillator, a spring, as it goes up and down, ooh, and it's going pretty quick. So that's a shorter period, right? A shorter period for this. In fact, it's going very frequently. So just a reminder from last time, we said frequency was the number of cycles in a second, which is equal to the number of hertz. So 1 hertz is 1 cycle per second. I think we had that last time. I hope that's review. I think it's review. When I was your age, we used to listen to radio, you know? We'd get CKLW from Windsor, Ontario. And they'd come on every once in a while and say, "This is CKLW broadcasting from 23 megahertz." Okay? So 23 megahertz. So it was 23 million hertz. And remember, these are radio waves, which is a type of light. We'll come back to that when we get to light in a month or so. And so I had 23 million light waves coming through my transistor per second. So it's cycles per second. So if it's light, it can be a lot of cycles in 1 second. Sound, less so. And a harmonic oscillator, even less. If I let this go, I can sort of estimate it. A second is like saying 1001. And I wish I could hold this stiffly. There, that's not too bad. Maybe I could do better if I use a pen. Let's put it on here. I knew this would be a problem. Okay, so what if I have it on my pen? Does that help? Let's find out. Doesn't if it slips off. That's not bad. So 1001. So it's somewhere between 2 and 3 cycles in a second. 1001. Or you could say 1 Mississippi. 1 Mississippi. It's about 3 cycles in a second, maybe. Okay, so that's its frequency, right? So its period would be about 1/3 of a second, about 1/3 of a second for 1 cycle. Okay, because what we learned last time is the period and the frequency is f, and the period was the time for 1 cycle. So they're like reciprocals. So we said, oh, period, which is a capital T, think of T as in time, and that's in seconds. So T is equal to 1 over the frequency, and frequency equals 1 over the period. Good equations to know. You'll need them for a problem set, which I'm going to assign here for next week. Okay, beautiful. So we need to talk a little bit about Hooke's law. Okay, you'll see why. An oscillating spring is a special thing. Let me ask you a question before I go on. Where do you guys know springs from? Where are springs found? They're found where? Can you give me some examples? Where do you find springs in the world? And what sort of human-made objects? In pens, exactly, Aunt Sophie. So if I go click, click, and my pen click, click, it's got a spring in it. Right, and Zach had the same thing. Good. So y'all have used it in pens. What about in vehicles? Vehicles. And I don't, Aunt Sophie, I don't know what your question is either. I don't know what P over P means. So it's period is in seconds, and it's so the time for 1 cycle. And T equals 1 over F, F equals 1 over 2. Okay, let's come back here. Clocks, shocks. You got it, Zach. So in a lot of shock absorbers, including in the S-Bahn and in a car. And in a car, they're really big suckers. They're big springs that are in a car shock absorber, okay? Good. So springs are rather important. And bicycle shocks too, yes. Not always, but some of those have big springs in them too. Right. Yeah, traditional watches like this one right here. That might have some springs in the back. Probably does. Probably does. Yeah. Well done. Okay, good. So I want to have us know some things about springs. And here's the main thing we need to know. It's called Hooke's law. And I'm going to show it to you, and then we're going to write it as an idea. Hooke's law. Robert Hooke was an English physicist who studied springs and a lot of other stuff too. So instead of making there goes my pen. Instead of making the spring oscillate, let's do it this way. Hey, that might be more clever. Instead of making the spring oscillate, he did something else. Okay. What he did, and this is going to be hard for me to do, but I'm going to try it and show you. Oh man, I wish I had more than 1 square meter here. Okay, what I got, everybody, is a bunch of masses, and I'm going to attach these on here and predict for me what's going to happen. I'm going to add some masses to the spring, and I'm not going to have it moving, at least not on purpose. What's going to happen to the length of this string when I add more mass? Aha, I'll add another. Maybe not a big surprise. What's happening as I add more mass? You got it. The spring elongates. That's a good way to say it. Yeah. And what we call the elongation is this. There's the length of the spring as it's unstretched. And if I stretch it out, then the difference between when it was stretched and unstretched, that's called the displacement. And I need us to know what that is. So I'm going to write that down for you, not in pen, but in marker. Okay, so for Hooke's law, we need to know about the displacement. We have that word with motion, and it really means, if you think about it, the same thing. So it's the difference in this point, difference in length between the initial and final position. Difference, how about DIFF? Difference in length between initial and final. Initial, I could spell today, and final position. So what I'm getting at, let me erase the stuff at the top here. And yeah, we've done a lab, and I don't know if you did it with me and Sophia another year. I don't think we've done it yet this year. I hope not, or I'm losing my mind. But the idea with a spring is if I put let me get this right. Okay. Oh man. Okay. I think the force is here. Now, I know you might say, but Mr. White, you put mass on. Well, remember, the more mass, the more force. In fact, I could measure this and see what it is in newtons. I brought a Newton scale just to remind us. Okay, so for example, my total mass I had on the sucker was 4 newtons. And if I take them off one at a time, I probably get like around 3 newtons. Let's see. Yeah, around 3 newtons, around 2 newtons, and around 1 newton with no extra mass on, just the initial contraption. Well, I've done this as a lab before, and maybe Anne-Sophie had this another year with me. And it's not really a hard lab. We say the force in newtons, the more force I put on the spring, the greater the displacement in meters or centimeters or whatever. I'll say meters. And if you do the lab, what you find out is it's linear. So I get this. Ready? I hope that's a line from your point of view. And let's see it. Yeah, Hooke's Law lab with springs. You can measure it in newtons. Exactly. So you've done this already, Anne-Sophie. Okay, so you don't really need the lab. Others, I'm sorry if you haven't done a lab, but here's kind of the thing. Okay, so it's linear. And it depends on the string, the spring. If I had here a stiffer spring, so here's my question for everybody. If I had a stiffer spring and I put the same masses on, what would happen to the displacement if the spring was stiffer? Would the displacement be more or less? What do you think? Stiffer spring. So we're going to plot it on the graph. That's why I ask. Would the displacement be more or less if this was stiffer? Think of like a shock absorber type spring, really thick and a stiff spring. It would be less. Yep, you're all right. Yes, exactly. So what that means is if I add force, my displacement is going to be, or how to say it this way. If I add force, my displacement is less, so it's kind of down here. So this would be a stiffer spring. Stiffer spring. Still linear, but a steeper line. And then if I had a really wimpy spring, it would, of course, be in some sort of line like this. But even so, it doesn't matter. What I want you to know, well, it does matter, but it's all a linear relationship. So what that means for you and I is Hooke's law says, in words, the greater the force, the greater the displacement on a spring. Not a big surprise, I know, and it's linear. Greater force means greater displacement of a spring. And it turns out the slope of this line has a special meaning. The slope of this means the stiffness of the spring. So look at if I have a gentle slope, okay, it's less of a, oh man, I am so sorry. I was busy with unstopping a toilet, so I'm exactly kind of like still in my my mindset of fixing things. Okay, so let's come back to physics. So the slope of this line is lower, so it's less of a number. So if the slope is less, then the stiffness is less. And if the slope is greater, the stiffness is greater. So what we call that for springs is called the spring constant. So a spring constant, and physics uses a small k for this, is a rough measure, well, not a rough measure, is a measure of a spring's stiffness. And it's in, you ready? K is measured in, not surprisingly, newtons per meter. Oh, as if I got a slope of one of these lines. So the slope of this line, or any of these lines, the slope is K. So that's the spring constant, the slope on this graph. Well, to make it then a long story even longer, let's give you what Hooke's law is in letters. I know I got a lot of stuff in your way. I'm dropping everything. See if you got any questions. Okay, so Hooke's law in letters is this. The force that I like hang from the spring equals to K times X. All right, so X is the amount of displacement. And interestingly enough, it's on the x-axis on my graph. Oh, nice way to remember it. So displacement is this x thing, okay? And it's in meters. So if you think about it, force is in newtons. That's in meters. K, if I divide by the displacement, I get newtons per meter. So it makes sense that K should be in newtons per meter as a label, okay? All right, why do we need Hooke's law? Because as it turns out, Hooke's law has to do with just the more I hang on my spring. My spring is now gone. Where'd it go? So Hooke's law, greater force on the spring, the greater that sucker displaces. Sure enough, it's working. And it's in a linear way. Oh yeah, longer, the more newtons, as it were, I put on here, right? If I measure these suckers with a spring scale. But now we're going to make the thing oscillate, and we still need the law. You'll see why we need Hooke's law. But now I'm going to take this. Ready? Watch this. Whoa. Okay, so now suddenly it's back to being a harmonic oscillator like we talked about last time. And interestingly enough, watch when I take some mass off. And I'm going to make it oscillate again. Oh, is it more or less frequent now? More or less frequent. And I'll take even more mass off while you're writing. I can't even get it going. There we go. More or less frequent, the oscillation. What does it say after slope? It says the slope is K, written badly here. Small k, the spring constant, is equal to the slope. It's more frequent. Exactly. Thanks, Ellie. Okay, so, and if it's more frequent, then the period is less and less and less. Thank you. Okay, so now we're going to get to some stuff you and I are going to do some problem solving with harmonic oscillators. We're going to do some now for our next 35 minutes. And then we're going to have you try some for an assignment that I'll have due sometime next week. So you have time to work on it. Okay? All right. So we need some equations. Okay. So I hope you've got this. F equals kx. There's an equation we need. I think I'm going to put it over here because I don't want to erase everything. So if I make the spring start to oscillate, to go up and down, here's an equation for that. So I want the period for an oscillating spring. Okay, well, period is t. And t equals, and because of my morning excursion, I'm so out of it, I'm going to make sure I give you the formula correctly. I know how many years have I taught physics, but I don't want to screw up. So I'm going to look it up and make sure I write down the right thing for you. And it is 2 pi. Everybody likes pie, right? Place to eat. Times the square root of m over k. All right, the k is the spring constant from Hooke's law. Ah, that's why we needed Hooke's law, okay? M is the mass in kilograms. What about that 2 pi? I want to show you something. I'm going to do something really goofy. And I'll do it with the back of this sheet. Can I attach this in here? I hope I can, because that's what I want to do. Oh, yeah, look at this. Okay, see that? We're going to make this thing go up and down. Okay, now imagine this thing going up and down. Okay, so let's say I put some mass on my magic marker and I have this going up and down. Okay, pretend it keeps going up and down, right? Up and down, up and down, up and down, up and down. Ready? I'm going to take the paper. Ready? Up and down, up and down, up and down, up and down. Whoa! If I draw the up and downness and pull the paper along, I get what sort of thing from math class? What is that from math class? So that's just by going like this. Here, that was going up and down, and I just pulled the paper across. So what did I get from math class? You still out there? Yeah, you're thinking. Okay. Yeah, I got a sine or cosine wave, exactly. And sine and cosine repeats every 2 pi. That's why there's a factor of 2 pi in there, okay? So the 2 pi has to do with the up and downness of the harmonic motion. The k makes sense because it's a spring, and if it's a stiffer spring, that's going to make the period. Actually, if you think about it, it's down at the bottom. So if I have a bigger number here, it's going to make the period. Oh, let's see. I divide by a bigger number. It's going to make the period shorter if I have a stronger spring. Yeah. Okay, and the mass, well, the more mass, the more period. And we saw that, didn't we? We saw the more mass, if I had a whole lot on it, kind of went, Now, if I had a little bit, it went beep, 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 beep. Okay? So mass is directly related to the period, the amount of time to go up and down. And it's indirectly related to the spring constant, and all of that's under a big square root. Good, we're going to use that here in a little bit. But you need one more equation. But yeah, it's a sine curve type of equation. The other one you need is for something we already studied, and that was if I make this into a pendulum. So we need the period of a pendulum, which, alas, since we're not at school, I can't have you do it, but sometimes I do a really big lab with you guys building a lot of pendulums. So I'm sorry we're going to miss that. But I have a pendulum, which we drew last time. So pendulum going back and forth. So the period of that, remember, period is the time for one trip out and back. That would be the period. So the period for a pendulum so that's also going to be t. T is in seconds. And by the way, check this out. Remember what a pendulum does. Bing, 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 bing. Now, put a pin here. Ding, 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 ding. And now pull the paper up. Ding, 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 ding. I get another sine wave. Ah! So if a pendulum goes back and forth, I get a sine wave if I pull this thing up. So by God, guess what? For the period of a pendulum, there's also another factor of 2 pi. We say, you ready for this? It's a periodic function. Get it? Period of a pendulum. Period. Never mind. Okay, so. And it's times the square root of. So this time it's related to a couple other things. Turns out with the pendulum, it matters a lot to the length of the pendulum. I'll put that as a big capital L. Divided by something that's hard to like imagine. What else could be important? And I want to make sure I'm remembering correctly. I'm 99.9% of the way sure. But why not just make it 100 and look it up? And I'm right. Okay, so, and what really matters is what planet you're on. Now, you and I don't really have a lot of worries. We're going to stay on this planet. But people have done pendulum experiments on the moon and found out that the law still works, but you got to put in a different number for moon's gravity. So for G, it's the gravitational acceleration. Gravitational acceleration. And we know what that is on Earth, right? So 9.81 meters per second squared. So Earth, 9.81, what we dearly love, meters per second squared. And L is the length of the pendulum in meters. Let me read all that because I know it's gotten a little small. Okay, so equation, period of a pendulum is the period equals 2 pi times this big square root of the length of the pendulum, L, over G, the gravity's acceleration value, wherever you're at, probably on Earth. And if it's Earth, 9.81 meters per second squared, the length is in meters. It's really blurry. Good. I will try and pull this over so it's less blurry. Maybe if there's less glare that way too, Anne-Sophie. How's that? I hope that helps. All right, I got to get some of this out of my way because I got so much crap sitting here. I can't even think. My tiny little physics lab, okay? My half a square meter physics lab here. Okay, let's put that over there. And we got markers, and that's really enough. Okay, I'm going to pause and see if you got questions while I look up, because I'd like to do now an example or two with you to see what we have time for. Ba-dum, 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 ba-dum. And really, pendulums are pretty easy. Let's do a harder one. Part in the bottom right corner. Let's just do it this way, Anne-Sophie. Ready? Here you go. Okay, so hopefully you can read all that, take a mental picture of it, and you can refer to the video later, hopefully, if I don't lose Wi-Fi with you. You got her there? Okay. All right, so let's get rid of some things, and let's do a problem. I find pendulum problems are a little easier. If we'll have time, we'll do a pendulum. But you know what? For now, we're going to do one with a oscillating spring. Okay? We're going to go and do a problem with Sam the Butcher. He's not like a mass murderer, don't worry. Sam the Butcher deals with chopped beef. So Sam puts 3 kilos, that's a lot, 3.0 kilograms of chopped beef. Where's the beef? Of beef on a 1.0 kilogram pan of his spring scale. Okay. And the scale constant of the scale, the spring constant, K, is 400 newtons per meter. Okay? Right. So let's find the period. 2 things. Find period of the scale. When meat is added. Okay. Well, let's see. Okay, so imagine here's the scale, and underneath it, it's got like this. Okay. So the more meat he puts on here, right? I'm going to put some like red meat on here. Sorry if you're a vegetarian. So the more meat on here, of course, the more the thing compresses. And maybe then it makes it go up and down a bit too. Remember, it's oscillating now. So he slaps it on and the scale goes. Okay. All right. Well, let's get our formula, right? So we said the formula is 2 pi times the square root of m over k. And that's what we want for part A. We want the period. What do I put in for m? What do you think? Read back through the problem. What do I put in for m? folks out there. So what will I put in for M, for the letter M in my equation here? Type in your best guess. Read the problem again. Yeah, exactly. So 4 kilos. Why? Because it's the meat plus the weight of the pan I got to put in there too. So 4.0 kilograms divided by the K, and they gave us that, so it's divided by 400 newtons per meter. Well, that's kind of a nice problem. It's really solved for you, isn't it? So you know what? Can you do 4 divided by 400? You can do that in your head, right? Wouldn't that be 0.01? Take the square root of that and multiply by 2 pi, and let me know what you guys get for the period. Please round it, and please put a label on it as well. So everybody pull out your calculator, punch, punch, punch. Let's see if we get the same thing, and then we'll do a little part B action. Okay, so you're finding the period. And let's get some agreement here. How do we round it, and what label goes on it as well once you do that? I would do 4 divided by 400 if I can't do it mentally. Then take the square root of that number, then times 2 times pi. Remember, it's got to be a number. You can't have it in terms of pi. That would be only in math class. Here I need like a decimal answer. For pi, you can just put in 3.14. Did I tell you guys how to memorize pi? Maybe I'll do that in a second. It's easy as pi. Sorry. Okay. Still waiting for an answer. Zach, Teresa, and Sophie, you can punch this out too. Don't wait out, Ellie. I need more than one of you to do it. So please do it, and let's get an answer, round it, and put a label on that sucker. I need your participation, because I'm kind of stuck right here. Okay. Are we still there? I think. My total physicers, physicurinen, are you still out there? Can you get an answer? Maybe it's taken a while. Maybe it's Pony Express. Good. Help out with the label, somebody. Help out with the label. Also, see if you get the same thing. Yeah, it's period. So somebody else punch in. What's the label of this sucker? Okay. The period of something. Yine. That's the answer, Anne-Sophie, but it's got to come out to a simpler label. So because it's newtons, a lot of that other stuff will cancel. Period is a measure of what. It should come out with what sort of label. And you're both right, and I'm glad you both agree. It is 0.63. And I'll wait. How about Teresa or Zach? What's the label if it's period? Look back on what period is. I need the label. I know it's got all this stuff, but this time you can just ignore that. The period has to come out in what sort of unit. It's not going to be a complicated thing. Okay, well, let's do it real quick. If nobody knows. So it's the square root of, you ready? Kilograms. A newton is a kilogram meter per second squared. But then I got another meter on top. No, I got a meter on the bottom. So you know what? The meters cancel. The kilograms canceled. And then I got like something over seconds. So really, yes, Aunt Sophia, and what time unit will it come out to be? If I got the bottom of the bottom is the second squared, then actually, and then I take the square root of that, and I'm going to get just what? Yeah, I got to get seconds. So even without doing this long thing, using the definition of a Newton, you can still say, oh, period, it's going to come out in seconds, okay? All right, part B. B for Sam, okay? B is a thinker, so everybody, even if you don't have a calculator with you. So for B, Sam adds more meat to the scale, to the pan. What happens to the period? Now it's just a qualitative answer. All right, look where it is in the answer. You're going to do what with the mass? And what effect will that have on the period? What do you think? Just look at it purely mathematically by looking at the formula. So more meat to the pan. So what happens to the period? The period will what? Waiting for 4 answers from all the 4 of you. Okay, I need Zach and Teresa. I need you guys to type in. Maybe you're having problems typing. I want to know that you're still there. Normally, you guys are good. Oh, that's a cool one. I like that. Let's do that next. Thank you very much, Aunt Sophie. So I got one answer, and it's right. So if I add more mass, they're across from each other, directly related, so the period will be greater. Right? It will be more seconds, more time. Yes, makes the fraction larger, or you could just say the time greater. So greater time. So here's the pan. Here's the pan. Here's the meat. Boo, boo, boo. Okay, here's some more meat. Boo, boo. Got it? Take the meat off. Boo. Okay? Put it on. Boo, boo. You ever had that with a spring? It's kind of cool. So the more mass, the greater the amount of time, the greater the period. Kind of makes sense if you think about it. That's why I like to act it out or draw a picture as well. So some of these you may want to draw a picture of the ones I assign you. Okay? Did I lose Zach or Teresa? I don't want to lose half my class. Okay. Then let's do one last one. I love it. This is hilarious. Daniela pushes her twin Daniel on a swing with a 2-meter rope. With what frequency will she have to push Daniel? That's kind of fun. Okay, so here we go. I'm going to erase this. Okay, so Daniela pushes. Let's not make it Daniel. That's too confusing. Let's make it Bob. on a 2.0 meter rope swing. How often will she have to push him? Oh, am I writing today? Come on. How often will she push him? Well, here's the tree. There's the tree limb. There's the rope. There's the swing. And there's Bob sitting here holding on. Hey, that's one of my better Bob picks. And there's this thing going back and forth, right? So the swing's acting like a pendulum. And here's Daniela back here. And she's going to push. And how often does she push him? Well, what are we really asking for? We're asking for the period. I didn't give you a lot of information, did I? But maybe I gave you enough. Check this out. The period of this pendulum, because that's what it is, it's a pendulum. You ever think about that? A swing is really a pendulum. Period is 2 pi times the square root of L over G. Well, we know all that, don't we? So it's just 2 pi times the square root of 2 meters. That's how long the rope is. Divided by your friend and mine, 9.81 from our friendly neighborhood Earth planet, meters per second squared. And that's it. Punch it out, gang. And you'll see how often Daniela here has to push her brother Bob. She's not pushing him off, no. Thanks, Aunt Sophie. Maybe you do that with your little brother. I don't know, but she's just gonna push him to like help him go higher. Okay. Don't do that with your little brother. Okay, so punch it out, everybody. 2 divided by 9.81. Take the square root, multiply by 2 times pi. Let's see what you get for the period of the swing, because that's what she needs to know, right? Every period goes by and then she pushes. Period goes by and she pushes. She's got to match that period. All right, let's see if everybody gets the same thing. So I got 2.84. Let's see if that's a check from everybody else. Can I see if I get a check? Thank you very much. So 2.84. Let's round it, maybe 2.8, huh? 2.8 seconds. Okay, what if I ask for the frequency? Here, let's let that be part A. B, frequency of this. Well, remember, frequency just equals 1 over the period. So that's easy. It's 1 over our answer here, 2.8 seconds. And could you guys get me the frequency? Probably be some kind of a fraction, right? Some sort of decimal. So get it as a decimal answer. Hey, there's Teresa and Zach. Thank you for punching it out. Just wanted to make sure you're still with us and see if you have any questions or anything. Okay, so find me the frequency and put the right label on your answer as well. So we need a different label. Frequency is not in seconds. So go back and look at your notes from earlier this hour. What is frequency in? So you can round it and then put the right label on. Yeah, but so far you guys don't have it. It's not in seconds. Not in seconds. Frequency is in another label. Hey, thank you, Zach. It is in hertz. And I think Zach has rounded it a little bit better. We need 2 places. So he's got 0.35. No, you rounded it right, Zach. It's 0.35, I think. We need 2 significant figures. 2.0 has 2, 0.35 has, remember the first 0 is just a placeholder. So 0.35, and then the label he has on it, Zach has hertz on it. Let me move that in the center so you can see a little better. I hope. Okay. So 1 over 2.8 seconds would be 0.35 hertz, big H, small z. Okay, yippee skippy. All right. Okay, here's what we're going to do. I'm going to assign you some problems for next week, but you can ask me some questions if you want tomorrow during the hour if you start them up. And also, if you run out of questions tomorrow, we're going to begin to talk about waves a bit. All right? So that's what's going on. Is it 0.36? Okay. 0.36. Thank you very much for checking it out. We'll round that sucker as such. So I'm going to wish you well the rest of your day. I'll see 2 of you later in AP Chemistry. And I'll save this in case you want to refer back to anything you might have missed. Okay? So be well, stay healthy, all 4 of you. And we'll see you tomorrow. We'll do a live stream tomorrow as well. Bye-bye.